a physicist who spent her entire career debunking UFO conspiracies, just admitted something that should terrify you. Sabine Hossenfelder, the woman who laughs at alien theories, just said we need to serious. We should consider that the interstellar object racing through our solar system right now might be alien technology. And Avi Loeb, the Harvard scientist everyone called crazy, might have been right all along. In 13 days, A3IATLAS reaches its closest point to the Sun. It either breaks apart like a normal comet, or it does something else entirely. But that is just the beginning. A 12,000-year-old sphere in Colombia responds to ancient Sanskrit chants. Congress just revealed footage of a UAP surviving a Hellfire missile. NASA found biosignatures on Mars, and AI just achieved something no human ever could. The next 60 days will either prove we are alone in a dead universe, or reveal we never were. Every scientist who dismissed this as impossible is about to be proven catastrophically wrong. If you're enjoying this deep dive into the mysteries unfolding right before our eyes, hit that like button and subscribe so you do not miss what happens next. Tell me in the comments where you are listening from, what time it is there, and whether you think A3IATLAS will break apart or release something on October 29th. The skeptic who changed her mind. Now let us talk about why. One of the most rational voices in physics just broke ranks with the entire scientific establishment. Sabine Hossenfelder is not your typical scientist who chases headlines. She built her reputation systematically dismantling pseudoscience, tearing apart UFO claims with the precision of a neurosurgeon, explaining why faster-than-light travel violates thermodynamics, why quantum consciousness is nonsense, why every grainy video of lights in the sky has a perfectly mundane explanation. She is the scientist other scientists point to when they want to shut down speculation, the rational voice, the skeptic, which is exactly why her latest video about 3IATLAS sent shockwaves through both the scientific community and the UFO research world. She did not just say the object is interesting. She did not hedge with maybes and possibly. She looked directly into the camera and said, "We need to seriously consider that this could be alien technology." Coming from Sabine, that statement carries the weight of a confession. It is like watching a career prosecutor suddenly argue for the defense. Something fundamental shifted in her analysis, and that shift tells us more than any individual data point ever could. Let us be clear about what happened here. Sabine reviewed the same papers every other astrophysicist has access to. She looked at the trajectory data, the spectroscopic analysis, the emission patterns. But where others saw anomalies they could explain away, she saw a pattern that made her uncomfortable. Not uncomfortable because the data is bad. Uncomfortable because the data is too good, too consistent, too deliberately strange. The video opens with her characteristic dry humor, almost apologizing for what she's about to say. She knows what this admission costs in academic circles. Suggesting alien technology is not just controversial, it is career suicide. You become the person nobody wants to collaborate with, the researcher whose grant proposals get quietly shelved, the name that gets removed from conference speaker. The stigma is real, and it is brutal. And yet, here she is, stepping into that minefield with full awareness of what it means. Her argument centers on something most people overlook when they think about scientific discovery. We focus on type 2 errors, false positives, believing something that is not true. Science has enormous machinery built around avoiding these mistakes. Peer review, replication studies, statistical significance thresholds. The structure of modern research is designed to prevent us from being fooled. But Sabine points out that we have almost no protection against type 1 errors, false negatives, rejecting something that is actually true. Think about that for a moment. Science is asymmetrically cautious. It would rather miss a genuine discovery than accidentally endorse a false one. That makes sense for most research. If you incorrectly claim a new particle exists, other scientists will eventually figure it out, and your reputation suffers. no permanent harm done. But what if the thing you are rejecting is not a particle or a theory? What if it is evidence of intelligent life beyond Earth? What if it is a spacecraft? The cost of a Type 1 error in that scenario is not just embarrassment. It is potentially catastrophic. If we dismiss alien technology because we're too afraid of being wrong, we might miss the single most important discovery in human history. We might fail to recognize a threat. We might ignore an opportunity for contact. And unlike a failed particle physics experiment, you do not get a second chance. The object passes through. We wave it goodbye, and we never know what we missed. This is the heart of Sabine's argument. She's not saying Oumuamua is definitely alien technology. She's saying the cost-benefit analysis of scientific caution is completely backwards when it comes to interstellar objects. We should be investigating as if it could be artificial, because the stakes are too high to default to the comfortable explanation. But here's where it gets interesting. Sabine does not just make a philosophical argument. She walks through the data point by point and shows why this object is genuinely unprecedented. Not unprecedented in the sense that it is a little unusual. Unprecedented in the sense that it breaks patterns we see in every other comet and asteroid we have ever studied. Start with the emissions. 3IATLAS is shedding nickel and iron at rates the papers describe as exceptional. Not high, not unusual, exceptional. That is scientific language. For we have never seen anything like this, and we do not have a model that explains it. Comets do shed material as they approach the sun. That is normal, but the composition and quantity here do not match what we expect from a natural icy body. Nickel and iron in these proportions suggest something else, something processed, something refined. Then there is the carbon dioxide to water ratio. Every comet we have studied has a predictable relationship between these two substances. Water ice dominates, with carbon dioxide mixed in at relatively low concentrations. 3IATLAS flips that script. It is pumping out carbon dioxide at 8 times the rate of water. That is not just unusual, it is backwards. Some researchers noted carefully that this ratio could fit what you would expect from exhaust, from a propulsion system venting gas as it maneuvers. Sabine does not claim that is what is happening, but she points out that when you see a ratio that looks like exhaust, acts like exhaust, and appears in an object moving on an unusual trajectory, maybe you should consider the possibility that it is exhaust. The light polarization data adds another layer of strangeness. When sunlight reflects off an object, it creates a polarization pattern that tells us about the surface composition and structure. Asteroids and comets have characteristic signatures. We've observed thousands of them. 3IATLAS shows a polarization pattern the researchers called unprecedented. Among asteroids and comets, that phrase appears in a peer-reviewed paper. Not unusual, not rare, unprecedented. What does that mean in practical terms? It means the surface of 3IATLAS is reflecting light in a way that does not match any natural object we have seen. The pattern suggests a surface that is either incredibly smooth or structured in a way that natural processes do not produce. Think about the difference between a river rock, worn smooth by water over centuries, and a ball bearing machined to precise tolerances. Both are round, both are smooth, but they reflect light differently, because one is the product of random erosion, and the other is the result of deliberate engineering. The tail pointing toward the sun is perhaps the most visually striking anomaly. Comet tails point away from the sun, always. It is one of the most basic facts of observational astronomy. The solar wind pushes gas and dust away from the nucleus, creating that characteristic streaming tail that always points in the opposite direction from our star. 3IATLAS has a tail pointing toward the sun. Researchers describe this as not common and possibly observed for the first time. That level of hedging in a scientific paper translates to, we have absolutely no idea what is causing this, and it should not be possible. Some have suggested magnetic fields or unusual outgassing patterns could create this effect. But those explanations require conditions we have never observed in any other comet. You can explain anything if you're willing to stack enough unusual conditions together. At some point you have to ask whether the simplest explanation might be that the object is not behaving like a comet, because it is not a comet. Sabine also points to the trajectory, though she is more cautious here. 3IATLAS is moving almost exactly in the plane of our solar system, within about 5 degrees of the ecliptic. For a random interstellar object, that alignment has about a 1 in 500 chance of happening naturally. Not impossible, but improbable enough to notice. It also makes close approaches to Mars, Jupiter, and Venus, 3 of the most significant bodies in the inner solar system, while staying far from Earth. If you were designing a reconnaissance mission, you might choose exactly this trajectory. Maximize observation opportunities of major planets, while staying clear of the one planet with active space infrastructure that might interfere with your mission. That is speculation, of course, but it is testable speculation. If 3IATLAS were artificial, we should see certain behaviors as it reaches perihelion. We should see controlled maneuvers, additional emissions, possibly detachment of small objects. If it is natural, it should break apart or show typical cometary activity. We're about to find out which scenario plays out. What makes Sabine's analysis so powerful is that she's not coming at this from a place of wanting to believe. She has spent years explaining why alien hypotheses are almost always wrong. She understands the overwhelming probability that 3IATLAS is exactly what most scientists think. It is a strange but natural object. But she also understands that being overwhelmingly likely is not the same as being certain. And when the stakes are this high, when we are talking about potential evidence of non-human intelligence, we cannot afford to let probability become dogma. The scientific community's response to her video has been telling. Some colleagues quietly thanked her for saying what they were thinking, but could not say publicly. Others dismissed it as attention-seeking, a respected physicist going off the rails for clicks. But the most interesting responses came from researchers who worked directly with the 3IATLAS data. They did not say she was wrong. They said she was premature. They want more observations, more analysis, more certainty before making any extraordinary claims. And that brings us back to the type 1 error problem. How much certainty is enough? At what point does demanding more data become a shield against uncomfortable conclusions? Sabine argues that the threshold for investigating something as potentially artificial should be much lower than the threshold for claiming it is artificial. Right now, most of the scientific establishment treats those two thresholds as identical. Unless you have proof beyond any doubt, you do not even mention the possibility. That attitude might have made sense when interstellar objects were theoretical curiosities, but we've now observed 3 of them in less than a decade. They are not rare, they're common, and if they are common and some unknown fraction of them could be artificial, then we are playing a game where the cost of skepticism might be higher than the cost of investigation. October 29th is 13 days away. That is when 3IATLAS reaches perihelion, its closest approach to the Sun. Every telescope available will be watching. Ground-based observatories, space telescopes, and ESA's JUICE spacecraft will all gather data. If the object behaves like a natural comet, it will likely fragment or show increased outgassing. If it behaves like something else, well, that is when things get interesting. Lullaby has been saying for weeks that November and December will be critical if 3IATLAS survives perihelion intact and continues to show anomalous behavior. The natural comet hypothesis becomes much harder to defend. If it breaks apart spectacularly, the skeptics will claim vindication. Either way, we're about to get more data than we have had for any previous interstellar visitor. But the real question Sabine is asking is not what 3IATLAS is. The real question is what happens to science when we are too afraid to consider uncomfortable possibilities. What happens when the social cost of being wrong about aliens becomes so high that we would rather risk missing first contact than risk looking foolish. That is not science. That is conformity dress. Sabine Hossenfelder just risked her reputation to say that maybe, just maybe, we should look at this object with open eyes instead of closed minds. The fact that such a statement requires courage tells you everything you need to know about the state of the field. And the fact that she felt compelled to make it anyway tells you how seriously she takes the data. In 13 days, we will start getting answers. But the question has been raised is bigger than one object. It is about whether science can adapt to the possibility that we might not be alone, and whether we can do it before it is too late to matter. Chapter 2. What made Sabine break the 3IATLAS anomalies? So, what exactly did Sabine see in those scientific papers that made her break, with decades of careful skepticism? What data points were so compelling that a physicist, who built her career on debunking extraordinary claims, suddenly said we need to take the extraordinary claims seriously? Let us dig deeper into the specific anomalies, because the devil here is not just in the details. It is in the pattern. Any single strange measurement could be an instrument error, a calibration issue, a misinterpretation. But when you stack 5 or 6 impossible things on top of each other, all appearing in the same object, you start running out of mundane explanations. The nickel emissions deserve more attention than they have gotten. When the research team described them as exceptional, they were not being dramatic. They ran the spectroscopic analysis multiple times, checked their instruments, compare the readings against every known comet signature in the database. Nickel should not be present in these quantities. Think about what a comet is supposed to be. A dirty snowball, right? Water ice mixed with dust. Some carbon compounds, maybe traces of metals. The metals are there, but they are locked up in mineral grains. Tiny particles mixed throughout the ice. As the comet heats up, the ice sublimates and carries these particles away as dust. You get a little bit of metal in the spectrum, but it is minimal. 3IATLAS is not doing that. It is emitting nickel as if the metal itself is vaporizing, as if there is so much heat and such pure concentrations that the nickel is turning directly from solid to gas. That requires temperatures we do not see in normal comets. It also requires the nickel to be present in forms that can vaporize easily. In nature, nickel is almost always bound up in silicate minerals or iron-nickel alloys. To get pure nickel vaporizing off the surface, you would need industrial refining processes, or you would need a thermal environment so extreme that it is melting the object from within. Neither of those scenarios fits a natural comet, but both of them fit something artificial. A spacecraft with nickel components experiencing thermal stress, or a power system using nickel in some capacity, perhaps as radiation shielding or structural elements. The fact that iron is also present, but in different ratios than you would find in natural iron-nickel alloys, makes it even stranger. It is as if someone selected specific metals for specific purposes, rather than getting the random mixture nature provides. Now, combine that with the carbon dioxide problem. That 8-to-1 ratio of CO2 to water is not just unusual. It is thermodynamically bizarre. Water ice is more stable than carbon dioxide ice. In any natural comet forming in the cold depths of interstellar space, water should dominate. You can create carbon dioxide-rich comets under very specific conditions. If the formation environment is extremely cold, and carbon dioxide condenses before water gets a chance. But those comets should also be rich in other volatile ices, like methane and ammonia. 3IATLAS is not showing elevated levels of those compounds, just carbon dioxide way out of proportion to everything else. Several researchers have pointed out that this emission profile looks remarkably similar to chemical propulsion exhaust. Not identical, but similar enough to raise eyebrows. Carbon dioxide is a common byproduct of combustion. If you were burning hydrocarbon fuels, you would expect to see water vapor and carbon dioxide in the exhaust, with the exact ratio depending on the efficiency of the burn and the composition of the fuel. An 8-to-1 CO2 to water ratio would suggest a very carbon-rich fuel or a very hot, efficient combustion process. Again, that is speculation, but it is testable speculation based on the data we actually have. The alternative explanation requires us to believe that 3IATLAS formed under conditions that are vanishingly rare, that it somehow preserved those conditions for billions of years while traveling through interstellar space, and that it just happened to end up on a trajectory that brings it through our solar system at a time when we have the technology to detect it. Possible, yes. Probable. That is where the debate gets interesting. The light polarization data is where things get genuinely weird. Polarization is one of those properties of light that sounds abstract, but tells you enormous amounts about physical surfaces. When polarized sunlight hits an object, the way it reflects and scatters depends on the surface texture, composition, and structure. Rough surfaces scatter light in all directions, creating low polarization. Smooth surfaces create higher polarization because the light bounces off at more predictable angles. Metallic surfaces behave differently than rocky surfaces. Icy surfaces have their own signature. After decades of observing comets and asteroids, astronomers have built up a library of what normal polarization patterns look like. You can often identify the composition of an object just from its polarization signature, without ever needing to analyze its spectrum. It is a powerful diagnostic tool, which is why the 3IATLAS polarization data is so troubling. The object is producing a polarization pattern that does not fit any category. It is not behaving like bare rock. It is not behaving like ice. It is not behaving like a dusty mixture of the two. The pattern suggests an extremely smooth, highly reflective surface, but the spectroscopic data says the surface should not be smooth at all. Those two pieces of information are contradicting each other, and nobody has a good explanation for why. One possibility is that the surface has a very thin, uniform coating of some material that dominates the polarization signature, while the underlying composition shows up in the spectrum. That can happen naturally with frost, or with very fine dust settling uniformly across the surface. But 3IATLAS is actively venting gas and shedding material. Any frost layer should be disrupted. Any dust coating should be uneven, unless the coating is being actively maintained, unless something is continuously creating that smooth surface, despite the outgassing and particle ejection. That sounds like science fiction, but so did the idea of ice geysers on Enceladus until we found them. So did the idea of organic molecules in the atmosphere of Titan. So did the idea of liquid water on Mars. Sometimes the universe does things that sound impossible, until we actually observe them happening. The tail pointing toward the sun's probably the most visually dramatic anomaly, and it is the one that has generated the most creative explanations. Some researchers suggested that maybe the object is rotating in such a way that outgassing jets are creating thrust that pushes material forward instead of backward. Possible. But those jets would need to be incredibly powerful and precisely oriented. Other scientists proposed magnetic field effects, where the object's own magnetic field, or interaction with the solar wind, creates unusual particle trajectories. Also possible, but we have never seen magnetic effects that strong in any comet. The problem with all these explanations is that they require multiples, unusual conditions to occur simultaneously. Yes, you could have asymmetric outgassing. Yes, you could have magnetic field effects. Yes, you could have unusual rotation. But getting all three at once, and exactly the right configuration to produce a forward-pointing tail, while also explaining all the other anomalies, the probability space starts getting very narrow. Here's another way to think about it. If you were designing a spacecraft that needed to vent excess heat or reaction mass, where would you point the exhaust? Away from your direction of travel? Probably not, because that would slow you down. You would probably vent forward or to the sides, anywhere that does not create unintentional deceleration. A forward-facing plume of gas would look exactly like what we're seeing. It would look like a tail pointing toward the sun. The trajectory analysis is perhaps the most contentious point, because it involves a lot of statistics and probability arguments, and those can be manipulated to support almost any conclusion. If you are not careful, yes, 3IATLAS is moving almost exactly in the ecliptic plane. Yes, that is statistically unlikely for a random object, but is it unlikely enough to be meaningful? Have you calculated that the odds of a random interstellar object entering at that angle are about 1 in 500? Critics pointed out that we have only observed 3 interstellar objects, so having one of them show an unusual trajectory is not that surprising. Fair point, but then you have to factor in the close approaches to multiple planets. 3IATLAS passes near Mars, swings around toward Jupiter, and approaches Venus. All major observational targets, all places where you would want to gather data if you were surveying the solar system. The counter-argument is that, if this were a deliberately planned mission, why avoid Earth? We are the only planet with detectable technosignatures, the only place where intelligent life is obviously present. If aliens wanted to observe us, they would come closer, unless they do not want to observe us. Unless Earth is specifically not the target, unless the mission profile is designed to study planetary formation, atmospheric composition, magnetic field interactions, things that are better observed from a safe distance. Or maybe the trajectory is just a coincidence. Maybe we are pattern matching, seeing intention where there is only chaos. That is the default scientific position, and it is usually correct. Usually, but not always. What makes all of this so frustrating is that we could get definitive answers with better observations. We could send a probe to intercept 3I. At last, we have the technology. The Delta V requirements are high, but not impossible. We could get close-up images, compositional analysis, magnetic field measurements, all the data we need to distinguish between a natural object and an artificial one. But we are not going to do it. Not because it is technically impossible, because it is politically and financially impossible. Nobody wants to be the agency that spent billions chasing what turns out to be a space rock. So instead, we watch from a distance, squinting at pixels and arguing about spectral lines. We collect data that is just ambiguous, enough to support multiple interpretations, and we wait for the object to leave the solar system, taking its secrets with it. October 29th is when 3I at last reaches perihelion. That is when the object will be under maximum thermal stress from the sun. If it is a natural comet, that stress should cause visible changes, fragmentation, increased outgassing, possibly a complete breakup. If the structural integrity is poor, if it is something else, it might show different behaviors, controlled vent, trajectory adjustments, stable configuration despite the heat. We will be watching ISIS. JUICE spacecraft will observe the object throughout November. As it moves away from the sun, those observations will be crucial because they capture 3I, at last in its most active state, when whatever is causing the anomaly should be most pronounced. The data will not be released immediately. It will take weeks or months to process, analyze, and prepare for publication. By the time we see the results, the object will be on its way out of the inner solar system. But the real test is not what we observe in November. The real test is what the scientific community does with those observations. If the anomalies persist, if the object continues to behave in ways that do not fit natural models, will researchers seriously consider artificial origins? Or will they invent increasingly elaborate, natural explanations to avoid the uncomfortable conclusion? Sabine Hossenfelder is betting that the data will force the conversation, whether scientists want it or not. She is betting that the anomalies are real, persistent, and ultimately unexplainable without invoking something beyond conventional astrophysics. She might be wrong. The object might fragment spectacularly at perihelion and reveal itself to be exactly what most scientists think it is. But if she's right, if 3I at last makes it through perihelion intact and keeps doing impossible things, then we are going to have a very different conversation in December. than we are having now. And that conversation will not just be about one object. It will be about how we approach the question of alien technology, how we balance skepticism with openness, how we handle discoveries that challenge fundamental assumptions about our place in the universe. It will be about whether science can evolve fast enough to deal with a reality that might be stranger than we ever imagined. Because here's the thing that keeps researchers up at night. 3IATLAS is not unique. It is the third interstellar object we have detected. How many more are passing through that we miss? How many passed through before we had the technology to spot them? How many will come after? And if even a small percentage of them are artificial, what does that mean for humanity? Chapter 3, Avi Loeb, was right all along. The vindication. Avi Loeb has been called a lot of things over the past 8 years. Attention seeker, pseudoscientist, the alien guy. Harvard's embarrassment when he first suggested that Oumuamua, the first confirmed interstellar object, might be artificial technology. The backlash was swift and brutal. Colleagues distanced themselves. Papers he submitted faced unusually harsh peer review. Conference invitations dried up. The scientific establishment made it very clear that speculating about alien spacecraft was not acceptable, even from a tenured professor at one of the world's most prestigious universities. Now, with 3IATLAS, displaying behaviors that make Oumuamua look ordinary by comparison, that same establishment is starting to use language that sounds suspiciously similar to what Loeb was saying back in 2017. Unprecedented, exceptional, difficult to explain with conventional models. They're not calling it alien technology yet, but they're running out of conventional explanations, and Avi Loeb is not being quiet about it. His response to the 3IATLAS data has been characteristically bold. Within days of the discovery, he published a paper asking the question directly: is the interstellar object 3IATLAS alien technology? Not, could it be, is it? That framing alone was enough to generate controversy. You're not supposed to ask that question in a scientific paper, unless you have definitive proof. But Loeb argues that is exactly backwards. You should ask the question as soon as you have sufficient reason to investigate, not after you already know the answer. The paper itself is fascinating, because it does not just speculate wildly. It lays out specific criteria for distinguishing natural objects from artificial ones, and systematically evaluates 3IATLAS against those criteria. The results are uncomfortable. For anyone committed to the natural origin hypothesis, start with acceleration. Natural objects in space follow predictable paths, determined by gravity and their initial velocity. If you observe an object long enough, you can calculate its trajectory with extraordinary precision. 3IATLAS is not following the calculated path. It is showing small, but measurable deviations that suggest non-gravitational acceleration. Now, comets can do this too. Outgassing creates thrust. As ice vaporizes and jets of gas shoot off the surface, they push the comet slightly off course. We've observed this effect in dozens of comets. We can model it, we understand it, but the acceleration profile of 3IATLAS does not match the outgassing pattern. The thrust appears more consistent and directional than you would expect from random jets of vaporizing ice. Loeb calculated that if the acceleration continues at current rates, the object will be moving about 0.00006 astronomical units per day squared, faster than gravity alone would predict. That is tiny. That is within the margin of error for our observations. But it is also exactly what you would expect from a spacecraft, making small trajectory adjust to maintain a specific course. Critics immediately pointed out that Comet 2I and Borisov, the second interstellar object, also showed non-gravitational acceleration. So clearly this is just normal cometary behavior, and Loeb is making mountains out of statistical noise. Fair point. Except 2A Borisov showed all the other signs of being a comet. It had a massive coma, a clear dust trail, spectroscopic signatures. that matched known comets from our solar system. It looked like a comet, acted like a comet, and when we calculated the acceleration it was causing through outgassing, the numbers matched. 3IATLAS does not match. The acceleration is there, but the outgassing that should explain it is not sufficient. Then there is the question Loeb keeps asking, that nobody wants to answer. If 3IATLAS is just an unusual comet, why is it aligned in its close approach to the Sun with the moment when Earth is just on the opposite side of our star? October 29th is not random. It is precisely timed so that when the object is at its brightest, when it is under maximum thermal stress, when whatever is causing the anomalies should be most obvious. We cannot observe it directly. We have to rely on spacecraft that are not on Earth. We have to wait for the object to emerge from behind the Sun before we can get good ground-based observations. Again, Loeb suggests this could be intentional if you wanted to conduct operations near the Sun while minimizing observation from Earth. This is exactly how you would time your approach. Position yourself so that the Sun blocks direct observation from the planet. With active space infrastructure, do whatever you need to do while hidden behind 200 solar radii of burning plasma. Then continue on your way before anyone gets a clear look. That sounds paranoid. It sounds like conspiracy thinking. But Loeb backs it up with probability calculations. What are the odds that a random object would happen to time its perihelion to coincide with Earth, being on the far side of the Sun? Not impossible, but low enough that you notice. Add that to all the other low probability features of this object, and the cumulative odds start looking very suspicious. His most controversial claim involves the dark forest hypothesis. This is an idea from science fiction, specifically from Liu Cixin's novel, The Three-Body Problem, but it is based on game theory that actual scientists take seriously. The hypothesis goes like this. The universe is full of intelligent civilizations, but they stay silent because broadcasting your presence is dangerous. Any civilization advanced enough to receive your signal is also advanced enough to be a threat, so everyone stays quiet, hiding in the dark forest of space, listening but never speaking. Any civilization that reveals itself gets eliminated by those who prefer silence. Loeb suggests that if 3IATLAS is artificial, it might be operating under dark forest protocols. Observe, but do not interact. Gather data, but do not reveal yourself. Stay far enough from Earth that you do not trigger active defenses, but close enough to the inner planets that you can conduct meaningful surveillance. It's a reconnaissance mission designed to go unnoticed. The fact that we noticed anyway is either a failure of their stealth or an indication that they do not consider us threatening enough to hide from. That is where most scientists stop taking Loeb seriously. Dark forest scenarios sound cool in novels, but applying them to real objects requires assuming things we have no evidence for. It requires assuming alien civilizations exist, that they care about us, that they operate according to principles we can understand, and that they are actively watching our solar system. That is a lot of assumptions stacked on top of each other, with no empirical foundation. But here is what makes Loeb difficult to dismiss entirely. He's not just making up stories. He's proposing testable hypotheses. If 3IATLAS is a spacecraft operating under dark forest protocols, it should behave in specific ways as it approaches perihelion. It should not fragment. It should maintain structural integrity despite thermal stress. It should possibly release smaller objects that disperse to multiple destinations. And it should accelerate away from the Sun, faster than gravity alone would predict, demonstrating active propulsion. All of those predictions can be tested in the next few weeks. If 3IATLAS at last fragments like a normal comet, Loeb is wrong and we can all move on. If it does not fragment, if it does any of the things he predicts, then we have a serious problem, because at that point, the natural explanations become increasingly contrived, while the artificial explanation becomes increasingly plausible. Loeb has also been talking about the mothership hypothesis. This idea suggests that 3IATLAS is not a single object, but a carrier for smaller probes As it passes through the inner solar system, it releases these mini probes to study multiple targets simultaneously. Each probe is small enough to be difficult to detect, but large enough to carry sensors and transmitters. They disperse to different planets, gather data, then either rendezvous with the mothership or continue independently into interstellar space. This is not pure speculation. It's based on how we would design an interstellar mission if we had the technology. You would not send one massive probe to one target. You would send a mothership that deploys multiple, smaller probes to multiple targets. More efficient, more robust, better science return if we would do it that way. Why assume aliens would not? The challenge is detecting those mini probes if they exist. Something the size of a refrigerator or smaller, moving on an independent trajectory, would be nearly impossible to spot with current telescopes, unless we knew exactly where to look. But Loeb has a plan for that too. His Galileo project has observatories in Massachusetts, Pennsylvania, and Nevada, specifically designed to track anomalous objects in Earth's atmosphere and near-Earth space. If 3IATLAS releases anything in our direction, Galileo Project telescopes will be watching. November and December are going to be critical months, not just for 3IATLAS observations, but for what Loeb calls enhanced UAP monitoring. He expects that, if there is any connection between 3IATLAS and the unidentified, anomalous phenomena that military pilots keep reporting, we should see increased activity during and after perihelion. If the mothership hypothesis is correct, if many probes are being deployed, some of them might enter Earth's atmosphere to gather data. The Galileo project will be looking for exactly that kind of activity. Critics say this is mission creep. You started with an unusual comet, and now you're predicting alien probe swarms in Earth's atmosphere. Where is the evidence? Where is the logical connection? But Loeb points out that we are not looking for evidence of separate phenomena. We are looking for evidence of one phenomenon, manifesting in multiple ways. If there is non-human intelligence operating in our solar system, it would not just announce itself politely. It would conduct operations across multiple domains, space-based observations, atmospheric surveys, possibly even surface monitoring. Connecting those dots is not conspiracy thinking. It is basic operational analysis. The scientific community's response to Loeb has evolved in interesting ways. In 2017, when he suggested Oumuamua might be artificial, the response was almost uniformly negative. Colleagues called him reckless, irresponsible, damaging to the field. Now, with 3IATLAS showing even stranger behaviors, the responses are more nuanced. Some researchers still dismiss him entirely, but others are quietly admitting that, while they would not phrase things the way Loeb does, they also do not have good natural explanations for what they are seeing. That shift is significant. It suggests that even among scientists, deeply invested in conventional explanations, the 3IATLAS data is causing doubt. They're not ready to call it alien technology, but they are ready to admit that something weird is happening. And they do not understand what Loeb has been arguing for years, that we need to flip the burden of proof when it comes to interstellar objects. Instead of assuming everything is natural until proven otherwise, we should investigate everything as potentially artificial until we can conclusively rule it out. That does not mean believing every UFO story. It means applying the same rigor to the artificial hypothesis that we apply to natural hypotheses. Test both. See which one fits the data better. Follow the evidence wherever it leads. That approach makes many scientists uncomfortable because it feels like giving credibility to fringe ideas. But Loeb argues that is exactly the kind of thinking that causes type 1 errors. We're so afraid of looking foolish by investigating the wrong hypothesis that we would rather miss a genuine discovery than risk our reputations. That might be acceptable in other fields. In the search for extraterrestrial intelligence, it is potentially catastrophic. If Avi Loeb is right about 3IATLAS, if it turns out to be technology from another civilization, The implications cascade in every direction. It means we are not alone. It means interstellar travel is possible. It means other intelligences are actively exploring the galaxy, and we are one of their targets. It means everything we thought we knew about our cosmic isolation is wrong. And it means Loeb, the man who has mocked and marginalized for suggesting these possibilities, will have been vindicated in the most dramatic way possible. But here's the thing that keeps me thinking about this. Long after I should have moved on to simpler questions, even if Loeb is wrong about 3IATLAS specifically, he is right about the broader point. We're not taking the possibility of artificial interstellar objects seriously enough. We have no protocols for investigating them, no funding mechanisms, no institutional support. We are cosmically unprepared for a discovery that could happen any day. And when it does happen, we are going to wish we had listened to the guy everyone called crazy. For the Boogosphere mystery, ancient alien technology, while everyone is watching 3IATLAS race toward the sun, something equally impossible is sitting in a laboratory in Colombia, something that should not exist, something that fell from the sky 7 months ago, and has been getting stranger with every test. The Boogosphere appeared on March 2nd, 2025, over the rural town of Buga in Colombia's Valle del Cauca region. Witnesses described it zigzagging through the evening sky, moving in ways that aircraft do not move, that meteors cannot move. It struck high-tension power lines without exploding, without fragmenting, without even slowing down noticeably. Then it descended into an open field, where a local couple recovered it before authorities arrived. What they found was a seamless metallic sphere, roughly the size of a basketball, cold to the touch despite having just crashed through power lines, and covered in intricate symbols that matched no known language. The couple reported that the grass around the landing site died immediately, not burned, not scorched, just dead. 7 months later, nothing will grow in that 3-meter radius. The soil tests clean for radiation, toxins, heavy metals, but the vegetation is gone and it is not coming back. That detail alone should have made international headlines. A crash site that kills organic matter through some mechanism we cannot detect. That is unprecedented, but the media largely ignored it, because the story sounded too much like a hoax. Mysterious sphere from the sky covered in alien writing. Come on. Every UFO enthusiast has heard that story a dozen times. Except this time, the sphere is real. The tests are real, and the results are impossible. Let us start with the carbon dating results, because that is where the story shifts from weird to genuinely disturbing. In September, Dr. Stephen Greer announced that the University of Georgia's Center for Applied Isotope Studies had analyzed organic material extracted from inside the sphere, not from the surface, from inside. The sphere has 31 microscopic holes, each about 4 millimeters in diameter, precisely drilled with tolerances that would challenge modern manufacturing. Inside those holes are thread-like structures that researchers initially thought might be fiber optic cables to hold those threads in place. Someone used organic resin. The carbon-14 dating on that resin came back with a date of 12,560 years before present, plus or minus a small margin of error. Let that sink in for a moment. The resin anchoring what appears to be technological components inside a metallic sphere is older than the pyramids of Egypt, by 7,000 years older than Stonehenge, by 8,000 years older than the oldest known cities. This resin was harvested and processed before humans had invented writing, before we had developed agriculture, before we had discovered how to smelt metal. Dr. Greer was careful to note that the resin being the old does not necessarily mean the sphere itself is that old. Whoever built this thing might have replaced components periodically, using whatever materials were available at the time. That is actually more disturbing than the alternative. It suggests the sphere has been operational, has required maintenance, has been actively used for over 12 millennia. That implies continuity. That implies an organization or intelligence that persists across timescales we can barely comprehend. The alternative is that the sphere was built 12,500 years ago and has been sitting somewhere inactive until it was deployed or discovered earlier this year. That raises its own questions. Where was it? Who activated it? And why now? The resin samples contained foraminifera. These are tiny marine organisms whose shells can be carbon dated. Their presence tells us the resin came from a coastal environment, probably from ancient beach sand or sedimentary deposits. That detail is weirdly specific. If you were an advanced civilization building technology, why would you use resin contaminated with foraminifera? Unless you were working with materials available at the time. Unless 12,000 years ago someone was incorporating ancient sand into their manufacturing process. Because that is what they had access to. Critics have pointed out that carbon dating only works on organic material. The foraminifera could have gotten stuck to the sphere at any point. Maybe it sat on a beach for a while. Maybe it was buried in sediment. The age of the contamination does not tell us the age of the device. True, but that argument ignores the fact that the resin is inside the device, in precision-drilled holes, serving a structural function. It is not surface contamination. It is an integral component. Now let us talk about what happens when you play ancient Sanskrit mantras near this thing, because that is where the story transitions from archaeological mystery to active phenomenon. In July, researchers at Mexico's Instituto Politécnico Nacional conducted a series of experiments on the sphere. They subjected it to frequency sweeps ranging from 60 to 20,000 hertz, measuring electromagnetic responses across the spectrum. The sphere showed some activity at frequencies between 190 and 300 hertz. Interesting, but not extraordinary. Then someone suggested trying ancient mantras. The sphere reacted, not subtly, not ambiguously. It produced measurable vibrations, thermal increases up to 5 degrees Celsius, and electromagnetic pulses that peaked during specific phonetic patterns in the chants. The researchers repeated the experiment multiple times, with consistent results. When they played random sounds at similar frequencies, nothing happened. When they played script mantras tied to the symbols etched on the sphere's surface, the device activated. Let me be very clear about what that means. This is not someone claiming they felt energy or sensed a response. This is instrumented measurement, showing physical changes in temperature, electromagnetic fields, and mechanical vibration triggered specifically by linguistic patterns, preserved in ancient Vedic texts. The sphere is responding to information encoded in human language from thousands of years ago. One version of the experiment reported that when different frequencies were directed at the sphere, it generated an electric field. But when a woman chanted a specific Hindu Vedic mantra, the electric field dropped to zero, not decreased, dropped to zero, as if the mantra was a shutdown command, as if someone programmed this device to respond to specific linguistic inputs. The symbols on the sphere have been partially decoded, using artificial intelligence analysis and consultation with experts in ancient scripts. The markings resemble Proto-Sanskrit, a form of the language that predates classical Sanskrit by several thousand years. Anthropologist Agnieszka Sartori and industrial designer Jaime Davis-Kaya worked with AI, my tools, to interpret the message. The translation is not definitive, but the consensus interpretation reads something like this: the origin of birth through union and energy, in the cycle of transformation, meeting point of unity, expansion, and individual consciousness. That sounds like mystical nonsense until you think about it in technological terms. Origin of birth through union and energy. Could that be describing a power source? Nuclear fusion involves union of atomic nuclei and release of energy. Cycle of transformation could refer to energy conversion processes. Meeting point of unity might describe a singularity, or a convergence point in a field generator. Individual consciousness could mean autonomous systems. Artificial intelligence. I'm not saying that is definitely what it means. I'm saying the symbols are sophisticated enough to support multiple interpretations, and at least one of those interpretations describes advanced technology, using metaphorical language that would make sense to people 12,000 years ago. The sphere also displays symbols that match Ogam, the ancient Celtic tree alphabet, Mesopotamian cuneiform, and various runic scripts. That geographic and cultural diversity is strange. These writing systems developed independently, separated by thousands of miles and thousands of years. Finding them all on a single object suggests either remarkable cultural exchange that we have no record of, or a source that predates and potentially influenced all of these traditions. X-ray analysis revealed the internal structure, 9 microspheres arranged in a specific geometric pattern, surrounding a central component that researchers call the chip. The microspheres appear to be connected by those fiber optic threads, running through the precision-drilled holes. The structure looks functional. It looks like a circuit or network, nodes connected by transmission lines, but the materials and manufacturing techniques are beyond anything we associate with Stone Age cultures. This sphere's composition is 95% aluminum, with trace amounts of rare earth elements, including cerium, lithium, and neodymium. That is significant because aluminum is one of the most abundant elements in Earth's crust, but it is incredibly difficult to refine. Aluminum does not occur naturally in metallic form. It is always bound up in oxide compounds that require enormous amounts of energy to separate. We did not figure out how to produce pure aluminum until 1886. Before that, aluminum was more valuable than gold because we could not efficiently extract it from ore. Yet here is an object potentially 12,000 years old, made primarily of refined aluminum, with a precision alloy composition that includes rare earth elements we've only been able to isolate and utilize for about 200 years. The manufacturing process required to create this object should not have existed when it was made, unless it was not made by humans. The weight changes are another mystery that nobody has adequately explained. When the sphere was first recovered, it weighed approximately 4.5 pounds. Within weeks, that weight increased to 22 pounds. The increase was not gradual. It jumped in discrete steps, as if the device was accumulating mass or activating internal systems that added weight. Then the weight stabilized. No one has reported further changes, but the initial increase suggests the sphere is not inert. It is doing something. It is active. Some researchers have suggested the weight change could be explained by moisture absorption or a hidden internal mechanism, like a battery or fluid reservoir. But the sphere is sealed. There are no visible seams, no access ports, no way for external material to enter. The X-rays show internal structure, but no obvious reservoirs or voids that could account for 17.5 pounds of additional mass. Could it be a gravitational effect, some kind of a field that alters the apparent mass without changing the actual matter content? That sounds like science fiction, but we're already dealing with an object that responds to ancient mantras and was manufactured with the techniques that should not have existed. Maybe we need to expand our definition of what is physically possible. Dr. Julia Mossbridge, a cognitive neuroscientist and UAP researcher, has suggested the sphere might be a really cool art project, an elaborate hoax created by someone with access to advanced materials and fabrication techniques. That is the safest hypothesis, and the one that requires the fewest extraordinary assumptions. Someone made a mysterious sphere, planted it with a good crash story, faked the carbon dating somehow, and is now enjoying watching researchers scratch their heads. But that explanation struggles with the details. How did the hoaxer get access to precision manufacturing, capable of drilling 31 perfectly aligned 4-millimeter holes in a seamless aluminum sphere? How did they fake carbon dating at one of the most reputable isotope labs in the world? How did they kill the vegetation at the landing site through a mechanism that leaves no detectable trace? How did they program electromagnetic responses to specific Sanskrit mantras? Each individual element could potentially be faked with enough resources and expertise. Faking all of them simultaneously starts to require a conspiracy, larger and more sophisticated than the phenomenon it is trying to explain. The timing is what keeps pulling me back to this story. March 2025. The same year, Trisolaris was discovered. The same year, UAP sightings in Colombia increased dramatically. The same year, governments started releasing previously classified UFO documentation. These events are probably unrelated. Probably. But the synchronicity is notable. If you wanted to deploy technology to Earth while drawing minimal attention, you would do it during a period when everyone is already distracted by other anomalies. You would hide your signal in the noise. The booger sphere might be exactly what it appears to be: ancient technology that predates known civilization, technology that suggests either a lost human culture, far more advanced than we believed possible, or intervention from a non-human intelligence that was active on Earth during the end of the last ice age. Either possibility rewrites history. Either possibility demands serious investigation. Instead, we get silence from official sources. The Colombian government has not commented. International scientific organizations have not requested access to study the sphere. The story circulates in fringe media and conspiracy forums, while mainstream outlets ignore it. That might be appropriate caution, or it might be institutional blindness to evidence that does not fit comfortable narratives. The Younger Dryas period. 12,000. 900 to 11,000. 700 years ago was a time of catastrophic climate change. The planet plunged back into ice age conditions for over 1,000 years, disrupting the slow warming that had been occurring. Since the last glacial maximum, sea levels fluctuated dramatically, ecosystems collapsed, and according to some researchers, entire civilizations vanished, leaving behind only fragments and legends. Plato wrote about Atlantis, placing its destruction around 11,600 years ago, close to the end of the Younger Dryas, close to the date on the booger sphere's resin. Mythologies from around the world describe advanced civilizations, destroyed by floods, fires, and cosmic disasters during that same period. We have dismissed these as primitive explanations for natural disasters. But what if they were accurate historical accounts? What if the booger sphere is a remnant from one of those lost civilizations? What if it is one of the few technological artifacts to survive whatever catastrophe ended that world? Or what if it is not from Earth at all? What if 12,000 years ago, during the Younger Dryas upheaval, something visited our planet and left this device behind? A marker, a message, a piece of technology meant to be found when we became advanced enough to recognize it for what it is. Chapter 5. UAP Disclosure, 2025. The walls are crumbling. Something fundamental shifted in September 2025. The carefully constructed wall between official acknowledgement and public knowledge started developing cracks, not subtle hairline fractures, but deep structural failures that suggest the entire edifice might collapse. The congressional hearing on September 9th was supposed to be routine, another round of testimony about unidentified anomalous phenomena, another opportunity for lawmakers to express concern, while accomplishing nothing substantive. Instead, Representative Eric Burrison from Missouri played a video that changed the conversation entirely. The footage showed an MQ-9 Reaper drone operating off the coast of Yemen in October 2024. Standard surveillance mission, standard threat environment. Then, something appeared on the targeting camera, an orb, metallic, moving at impossible speeds. The drone operator made a decision. He fired a Hellfire missile. In case you are not familiar with Hellfire missiles, they are designed to destroy tanks. They carry a 20-pound warhead traveling over 900 miles per hour. When they hit something, that something stops existing in any meaningful sense. The orb took a direct hit. The explosion was visible on the infrared camera, and then the orb kept flying. Not damaged, not slowed. It continued on its trajectory, as if the missile had passed through empty air. Burleson did not speculate about what the orb was. He did not need to. The video speaks for itself. We have objects in our airspace that can survive, weapons designed to destroy armored vehicles, objects that move in ways that violate our understanding of propulsion and aerodynamics, objects that when engaged with lethal force simply ignore it. The Defense Department's response was telling in what it did not say. No denial that the footage was authentic. No explanation for what the orb was. Just a statement that they continue to investigate unidentified, anomalous phenomena with appropriate rigor, and that there is currently no evidence suggesting extraterrestrial origin. That last part is doing a lot of work. No evidence suggesting extraterrestrial origin is very different from having evidence suggesting terrestrial origin. It is the sound of an institution that knows something, but cannot figure out how to say it. 3 service members and veterans testified at that hearing about their own encounters. Air Force veteran Dylan Ballard described events at Langley Air Force Base in Virginia. For multiple nights in a row, objects appeared over the base, not distant lights, objects hovering at low altitude, clearly visible, demonstrating capabilities that no known aircraft possesses. Ballard reported the incidents through official channels. He was interviewed by ARO, the Pentagon's All-Domain Anomaly Resolution Office. His claims were dismissed. That dismissal is significant because Ballard is not a UFO enthusiast making wild claims. He is a trained observer with security clearance, reporting events that occurred over one of the most secure military installations in the United States. His testimony was detailed, consistent and corroborated by multiple witnesses. The fact that Rowe dismissed it suggests the office is not actually investigating these phenomena. They are managing them. There is a difference. Another witness testified about objects that ascended to commercial jet level and left the area at high rates of speed. Not helicopters, not drones. Objects demonstrating acceleration that would kill a human pilot through sheer G-forces. The witness went through proper reporting channels. Nothing happened. No follow-up. No investigation. Just documentation filed away where it would not cause problems. This pattern repeats across dozens of testimonies. Military personnel see objects doing impossible things. They report through official channels. The reports are acknowledged but not investigated. The witnesses are told to stop talking about it. In some cases, they face retaliation. Security clearance is revoked. Job opportunities vanish. The message is clear. You saw what you saw, but talking about it will ruin your career. The hearing revealed something else that has not gotten enough attention. The Pentagon is blocking access to information that Congress has explicit authority to receive. Representative Anna Paulina Luna from Florida chairs the House Task Force on the declassification of federal secrets. She has been trying to obtain UAP-related documents that should be available to oversight committees. The documents exist, they are cataloged, but every request gets denied on national security grounds or lost in bureaucratic procedures that make access functionally impossible. Luna pointed out the obvious problem with this. If you create an oversight committee, but then prevent that committee from accessing the information it is supposed to oversee, you do not actually have oversight. You have theater. You have the appearance of accountability without any actual mechanism for holding anyone accountable. The situation is complicated by the fact that some UAP sightings almost certainly involve classified military technology, secret drones, experimental aircraft, electronic warfare systems that create radar signatures that look. The Pentagon has legitimate reasons to keep those programs classified, but that classification creates perfect cover for hiding truly anomalous phenomena that might be far more significant. This is where the Wall Street Journal reporting from earlier this year becomes relevant. They investigated rumors about secret UFO programs and discovered something unexpected. Some of the rumors, the ones about recovered alien spacecraft and reverse engineering programs, those rumors were being generated and spread by Pentagon officials themselves, not by believers, not by conspiracy theorists, by the very people who should be investigating objectively. Why would the Pentagon spread rumors about alien technology? The journal suggested it might be disinformation, designed to protect classified projects. If people think a weird radar signature is an alien spacecraft, they stop asking about the actual classified drone program that created the signature. The alien cover story is so ridiculous that serious people dismiss it, which means they also dismiss the real, classified programs hiding underneath. But that strategy has a major flaw. If you train people to dismiss everything as either mundane, misidentification, or disinformation, what happens when something genuinely anomalous appears? How do you communicate that to decision makers, who have been conditioned to treat all UAP reports as noise? You create a system that cannot respond to actual threats, because it has spent decades teaching itself not to see. Colonel Carl Nell understands this problem better than most. At the Rice University archives of the Impossible Conference in 2025, he presented something that made even skeptics pay attention: a 5-phase disclosure roadmap. Not speculation, not wishful thinking. An actual operational timeline with milestones and objectives. Phase 1 prove UAPs exist. That happened in 2024, when the Pentagon officially confirmed that unidentified objects are regularly observed in restricted airspace and demonstrate capabilities we cannot explain. Done. Checked off the list. Phase 2 established that some UAPs demonstrate technology beyond current human capabilities. We're in this phase now. The Hellfire missile video is evidence for this phase. So are the multiple military encounters, with objects that accelerate at rates that would require propulsion, systems we do not possess. Phase 3 determined that at least some UAPs represent non-human intelligence. That is the controversial step. That is where institutional resistance is strongest. But Nell argues we're closer to this phase than most people realize. The evidence is mounting. The question is whether institutions can adapt fast enough to acknowledge it. Phase 4. Establish communication protocols. This assumes we reach Phase 3 and have confirmed that we are dealing with non-human intelligence. At that point, the question becomes, how do we communicate? What frameworks exist for interspecies or intercivilization contact? The answer is basically none. We are profoundly unprepared for this scenario. Phase 5. Engage with non-human intelligence. Nell places this after 2034, a decade away. But he also notes that the timeline could compress dramatically, depending on events. If 3IATLAS turns out to be artificial, we skip straight to Phase 3. If contact occurs through other means, the whole roadmap accelerates. What makes Nell's presentation remarkable is that he was not speaking as a UFO enthusiast. He's a career Army intelligence officer, a Pentagon UAP advisor, someone who has been in rooms where these discussions happen at the highest classification levels. When he presents a timeline for engaging with non-human intelligence, that is not speculation. That is operational planning based on classified assessments. The National Archives deadline of September the 30th. 2025 was another milestone that did not get sufficient coverage. Federal agencies were required to transfer all UAP records to the National Archives by that date. Not summaries, not sanitized versions. Complete records. The legislation establishing the Unidentified Anomalous Phenomena Records Collection specifically mandated this transfer to ensure public access. As of mid-October, most agencies have not complied. The records exist. The inventories have been compiled, but actual transfer to the archives has been delayed through various procedural mechanisms. That delay is not accidental. Someone decided that public access to these records is more dangerous than not. On compliance with federal law, what is in those records that justifies breaking the law to keep them hidden? We know from leaked documents and whistleblower testimony that the records include high-resolution images and video of unidentified craft. They include radar data, showing objects performing maneuvers that violate known physics. They include testimony from military personnel describing close encounters with non-human entities. They include analyses by scientists and engineers, who concluded that some of the observed technology represents capabilities centuries or millennia beyond current human understanding. If even a fraction of that material becomes public, the conversation changes fundamentally. Right now, UAP phenomena exist in a strange limbo, officially acknowledged but not officially explained, observed by credible witnesses but dismissed by institutions, studied by government programs, but with results kept classified. Public disclosure of the archive's material would end that limbo. We would have to confront the data directly. The Age of Disclosure documentary, which premiered at South by Southwest in March, interviews 34 government, military, and intelligence officials. Not conspiracy theorists, not UFO enthusiasts. People with security clearances and direct access to classified programs. They make extraordinary claims. The United States has recovered non-human craft. Multiple countries have similar programs. Russia and China are attempting to reverse engineer the technology. We've had this capability since the 1940s, but have kept it compartmentalized to the point where even presidents have limited access. Those claims require evidence. Extraordinary claims require extraordinary evidence, but the documentary does not provide physical proof. It provides testimony, consistent testimony from independent sources, describing the same basic reality. That is powerful, but it is not conclusive. We need the actual evidence. We need the photographs, the material samples, the engineering analyses. We need the stuff that is sitting in classified databases and storage facilities protected by security protocols that prevent even congressional oversight. Louis Zeldin and Christopher Malach have been central figures in this disclosure process since 2017, when they helped leak the Navy fighter jet videos showing unidentified objects. Elizondo claims to have run a Pentagon program investigating UAPs. He resigned in protest over excessive secrecy and internal obstruction. Since then, he's been lobbying Congress, briefing journalists and pushing for greater transparency. Elizondo has made specific claims that are either completely true or completely false, with no middle of ground, he says. High-ranking intelligence officials have discussed killing him to stop his disclosure efforts. He says the United States has multiple recovered craft in various states of completeness. He says some of these craft are operational or partially operational. He says non-human biologic have been recovered from some crash sites. Those claims are so extreme that they invite skepticism. But Elizondo is not a random person making YouTube videos. He had access to classified programs. He knows where the evidence is, and he's willing to testify under oath about what he knows. The question hanging over all of this is simple but profound. If even 10% of what these whistleblowers claim is true, why is it still classified? What national security interest is served by hiding evidence of non-human intelligence? The standard answer is that revealing our knowledge would expose intelligence sources and methods. Adversaries would learn what we know and how we know it. That is a legitimate concern for ongoing military operations. But recovered technology from decades ago, observations from the 1940s. What sources are we protecting? The alternative explanation is that the classification is not about protecting sources. It is about controlling narrative. It is about preventing societal disruption that might occur if people suddenly learn that we are not alone, that we are being observed, and that our governments have known about it for decades, while publicly denying everything. That might be a reasonable position if you believe the public cannot handle the truth. But it is also profoundly anti-democratic. It treats citizens as children who need to be protected from information, rather than adults who have a right to know what their governments know. 2025 is shaping up to be the year when that protective wall starts to fail. Not because of a single dramatic revelation, but because of accumulated pressure from multiple directions, congressional hearings that cannot be ignored, whistleblowers who refuse to stay silent, international disclosure from countries like Mexico and Peru that are releasing their own UAP files, scientific analysis of objects like 3IATLAS that defy conventional explanation, and most importantly, a growing recognition that the old system of denial and ridicule is no longer working. We are watching disclosure happen in slow motion, not the dramatic Hollywood version, where aliens land on the White House lawn, but the messy, real-world version where institutions slowly admit what they have been hiding, piece by piece, pushed by circumstances they can no longer control. The question is not whether disclosure will happen. The question is whether it happens through deliberate transparency or through catastrophic revelation that nobody can manage. Chapter 6. The Mars Biosignature. We found life. Last summer, NASA's Perseverance rover investigated what one mission scientist called the most puzzling, complex, and potentially important rock yet encountered on Mars. The rock showed signs of past water, organic material, and clues suggesting chemical reactions consistent with microbial life. That discovery was interesting. What happened next was extraordinary. After a rigorous, year-long peer review process, during which outside scientists scrutinized every aspect of the Mars 2020 team's data and analysis, the journal Nature published the validated results in September 2025. The Sapphire Canyon sample contains potential biosignatures, not definitive proof of life. Potential biosignatures, in scientific language. That phrase carries enormous weight. It means the evidence is strong enough to warrant that classification, even after intense skepticism from independent reviewers. Let me be very clear about what peer review means in this context. When you submit a paper claiming you might have found evidence of life on another planet, the reviewers do not give you the benefit of the doubt. They attack your methodology. They question your instruments. They demand alternative explanations for every observation. They look for any possible way your data could be explained by non-biological processes. The fact that the Sapphire Canyon paper survived that process and got published in Nature is, itself, a significant endorsement. The rock, Perseverance, sampled as part of a formation called Chiava Falls in Jezero Crater. The crater itself is significant because it once held a lake. We know this from orbital imaging, from the geology Perseverance has been mapping, and from the sedimentary structures that only form in standing water. But not just any lake, a calm, persistent lake that existed long enough for fine-grained sediments to settle and compact into mud. The kind of environment where on Earth microbial life thrives. Cheever Falls shows layering that tells a story of repeated water activity, not a single flooding event. Multiple episodes spanning potentially millions of years. Water came and went. The chemistry changed over time, and in those changing conditions, something left marks in the rock that look biological. The leopard spots caught everyone's attention immediately. These are small circular features, visible even in the rover's standard cameras, that pepper the surface of Cheever Falls rocks. Each spot is a few millimeters across, with a darker center surrounded by a lighter halo. On Earth, similar patterns are created by chemical reactions between rocks and fluids, reactions that are often mediated by microbial activity. The microbes do not create the spots directly. They facilitate chemical gradients that cause minerals to precipitate in circular patterns. The spots in Cheever Falls contain both iron phosphate and iron sulfide. That combination is significant because on Earth, even simple microbial life, the implications cascade through every branch of science. It means life is not a unique accident that happened once on Earth. It means the chemistry that creates life is common enough that it occurred independently on two planets in the same solar system. And if it happened twice here, it probably happened billions of times across the galaxy. That is the real significance of the Sapphire Canyon sample. Not that we might have found one instance of extinct microbes on Mars. That finding Mars had life makes it almost certain that life is everywhere. We stop being alone in the universe and become one example among countless others. That shift in perspective from unique to common is profound. It changes how we think about our place in the cosmos. But we need that sample back on Earth to be sure. We need to run tests that can only be done in terrestrial labs, with instruments that weigh tons and require specialized facilities. We need to rule out every possible abiotic explanation with absolute certainty, and we need to do it soon. While the scientists who collected the samples and designed the mission are still active in their careers, while institutional memory is intact, while we still have the political will to spend money on answering fundamental questions. Because here's the thing about big questions. The window for answering them is often smaller than we realize. Budget priorities shift. Political administrations change. Public attention moves to other concerns. The Mars Sample Return mission exists in a narrow window between having the technology to do it and having the resources to fund it. If that window closes, we might be waiting decades before it opens again. And in those decades, the most important scientific discovery in human history sits in a tube on Mars, unreachable, waiting. Chapter 7, Quantum Breakthrough. Reality just got weirder on October 7th, 2025. The Nobel Prize in Physics was awarded to 3 scientists who proved that the quantum world is not confined to the microscopic realm. John Clark, Michel Deverett, and John Martinez demonstrated that quantum mechanical effects can manifest in circuits large enough to see with your naked eye. That might not sound revolutionary until you understand what it means. They showed that the impossible is possible, that the boundary between classical physics and quantum weirdness is not where we thought it was, that reality at all scales is stranger than we believed. The work that won them the Nobel dates back to the mid-1980s, but its implications are only now being fully realized. Clark, Deverett, and Martinez built electrical circuits using superconductors, materials cooled to near absolute zero, where electrical resistance drops to zero. These circuits contained Josephson junctions, tiny barriers between superconducting materials, where quantum effects should theoretically occur. The question was whether those effects would scale up, whether something macroscopic could behave quantum mechanically. The answer was yes. Spectacularly yes. The circuits did not just show quantum effects, they showed quantum tunneling, one of the most counterintuitive phenomena in physics. In the classical world, if you throw a ball at a wall, it bounces back. The ball does not pass through solid matter. But in the quantum world, particles can tunnel through barriers that classical physics says should be impenetrable. Electrons do it constantly. Atoms do it under the right conditions. But macroscopic objects, a circuit you can hold in your hand, that should not be possible, except it is. The laureates showed that roughly 100 quadrillion electrons in their circuits could collectively tunnel through barriers in a coordinated way. Not one electron sneaking through. 100 quadrillion moving together as a quantum system. That is a redefinition of what we mean by quantum physics. It means quantum rules apply to much larger systems than we thought. And if they apply to circuits in a lab, what else might they apply to? Alexandra Blay, a quantum physicist at the University of Sherbrooke, said it perfectly. If you put yourself in the right conditions, quantum effects will emerge. That statement has profound implications. It means quantum behavior is not something exotic that only happens in particle accelerators or specially prepared experiments. It is latent in ordinary matter, waiting for the right conditions to manifest. Cool things down enough. Isolate them from environmental noise, and the quantum world appears at scales we can directly observe. Stephen Girvin from Yale called this discovery the beginning of quantum electrical engineering. Before this work, quantum mechanics was something for physicists. After this work, it became something engineers could use. You could design circuits that exploit quantum effects. You could build devices that operate according to quantum rules, while being large enough to manufacture and manipulate with conventional tools. The most obvious application is quantum computing. Every quantum computer currently under development uses principles derived from this Nobel Prize-winning work. Superconducting circuits with Josephson junctions form the basis of quantum bits, qubits, the fundamental units of quantum computation. Google's Sycamore processor uses them. IBM's quantum computers use them. These are not theoretical devices. They're functioning machines, processing real calculations using macroscopic quantum effects. But quantum computing is just the beginning. The same principles enable ultra-sensitive magnetometers that can detect magnetic fields 1 billion times weaker than Earth's magnetic field. Medical imaging relies on these devices. MRI machines would be far less capable without the quantum sensors made possible by this work. Gravitational wave detectors use quantum squeezed light to improve their sensitivity. Material science uses quantum principles to design molecules and crystals with specific properties. The technology enabled by macroscopic quantum effects is already embedded in systems we use daily. The October 13th announcement of a quantum version of Bayes' rule adds another layer to the story. Bayes' rule has been helping us make smarter predictions for 250 years. It is the mathematical foundation for updating beliefs based on new evidence. Every time your spam filter learns what you consider junk mail, it is using Bayes' rule. Every time a doctor refines a diagnosis based on test results, Bayes' rule is implicitly guiding that process. But Bayes' rule was developed for classical probability. It assumes information behaves in classical ways. Quantum systems do not behave classically. Their information is encoded in superpositions and entanglements that have no direct classical equivalent. So, how do you do Bayesian inference on quantum systems? Researchers at the National University of Singapore, Hong Kong University of Science and Technology, and Nagoya University figured it out. They derived a true quantum Bayes rule from first principles, using the concept of quantum fidelity to measure how much quantum states change when you update them with new information. This is not just an interesting mathematical exercise. It is a practical tool for quantum machine learning, for processing quantum sensor data, and for making predictions in quantum systems. Valerio Scarani, one of the researchers, called it a breakthrough in mathematical physics. Francesco Buscemi said they taught Bayes' rules quantum tricks. The understated language typical of scientific papers conceals something remarkable. They extended one of the most useful tools in probability theory into the quantum realm, opening pathways for AI systems that can reason about quantum information in ways that classical computers cannot match. On October 14th, another quantum breakthrough was announced. Scientists at the University of Cambridge discovered that organic molecules can exhibit quantum behaviors previously thought possible only in inorganic materials. Specifically, they found that certain semiconducting molecules can generate electrical charges through a quantum mechanism similar to what happens in high-efficiency solar cells, but using materials that are much easier and cheaper to produce. This discovery connects to research from 100 years ago. Neville Mott, a physicist whose work laid foundations for understanding how electrons behave in disordered materials, proposed ideas about charge separation that were considered important but limited to specific inorganic systems. The Cambridge team showed that Mott's principles apply to organic molecules as well. That means you could potentially build solar panels using printed organic materials instead of expensive crystalline silicon, lighter, cheaper, potentially more efficient in certain applications. The researcher leading the study noted it feels like coming full circle, connecting modern quantum discoveries with insights from a century ago. That is often how science progresses. Old ideas get re-examined with new tools and reveal depths that were not apparent at the time. Quantum mechanics has been doing this repeatedly in 2025, showing us that phenomena we thought we understood actually have hidden layers waiting to be explored. Fractional excitons represent another frontier being explored. Researchers at Brown University discovered these quantum particles in January, publishing their results in Nature. Excitons are quasi-particles that form when an electron and a hole, the absence of an electron, bind together in semiconductors. Normally, they carry integer charges. Fractional excitons carry fractional charges and follow quantum statistics that do not match any previously known particle class. Dima Feldman, one of the researchers, said this feels like having a finger on the knob of quantum mechanics. It is an aspect of quantum behavior we did not fully appreciate before. These particles could enable new types of quantum computation, new forms of information storage, and new ways of manipulating quantum states. We're discovering that the quantum world has more structure, more variety, more exploitable features than we realized even a decade ago. Entanglement, the phenomenon Einstein called spooky action at a distance, continues to be both a resource and a mystery. In July, researchers demonstrated something called an entanglement battery. The second law of thermodynamics says entropy always increases. You cannot reverse the arrow of time. Heat flows from hot to cold. Never the reverse, unless you input energy. But what about quantum resources like entanglement? Can you reverse the process of entanglement degradation? The answer is yes, with a clever trick. If you have an auxiliary quantum system, a battery, you can use it to reversibly manipulate entanglement in your primary system. You can take entangled particles, do operations on them that reduce their entanglement, then use the battery to restore the entanglement to its original state. This does not violate thermodynamics, because you're using the battery as a resource, but it shows that quantum resources can be managed in ways that have no classical analog. This has immediate applications in quantum communication and quantum cryptography. If you can reversibly manipulate entanglement, you can build more robust quantum networks, and you can correct errors without destroying the quantum information you are trying to protect. You can potentially extend the range of quantum communication links by refreshing entanglement along the way. In September, researchers at Kyoto University and Hiroshima University solved another long-standing problem. They figured out how to efficiently identify W states, a specific type of multiphoton entanglement. Entangled states come in different varieties. G-Has states were understood decades ago. W states were proposed at the same time, but identifying them required exponentially scaling measurements as you added more particles. That made them impractical for systems larger than a few photons. The Kyoto and Hiroshima team developed a method using cyclic shift symmetry that identifies W states with a single measurement. Regardless of how many photons are involved, this is crucial for quantum teleportation, where you need to reliably identify the entangled state before you can use it to transmit information. The breakthrough potentially enables quantum communication networks that scale to many nodes without losing efficiency. All of these developments share a common thread. Quantum mechanics is not just a theory about the very small. It is a theory about information, about how physical systems store and process information at the most fundamental level. And we are learning that quantum information processing is not limited to exotic laboratory conditions. It happens in biological systems. It happens in chemical reactions. It happens in materials at room temperature if you design them correctly. That has implications beyond technology. It affects how we think about consciousness, about how brains process information, about whether quantum effects play a role in biological computation. Those questions are still controversial, but the fact that quantum effects scale up to macroscopic systems and persist in warm, noisy environments means we cannot automatically dismiss quantum biology as impossible. The quantum computing timeline is accelerating. 5 years ago, quantum computers were laboratory curiosities capable of toy calculations. Today, companies like Google, IBM, and startups funded by billions in venture capital are building machines with hundreds of qubits. The quality of those qubits is improving. Error rates are dropping. Coherence times, how long quantum states remain stable, are increasing. We are approaching the point where quantum computers can perform calculations that classical computers cannot feasibly match. Skeptics argue that quantum computers have been 5 years away from practical usefulness for the past 20 years. Fair criticism. Hype has consistently outpaced reality in this field. But the Nobel Prize, going to the foundational work, the steady drumbeat of incremental improvements, the commercial investment, all suggest we are closer to a quantum computing inflection point than the skeptics believe. When that inflection arrives, when quantum computers become genuinely useful for real-world problems, the impact will extend beyond faster calculations. It will affect cryptography, making current encryption methods obsolete. It will affect drug discovery, enabling molecular simulations impossible with classical computers. It will affect material science, artificial intelligence, financial modeling, climate prediction, any domain where complex optimization or simulation is bottlenecked by computational limits. But perhaps the deepest impact will be philosophical. Quantum computers force us to confront what computation means. Classical computers manipulate bits that are definitely 0 or definitely 1. Quantum computers manipulate qubits that are 0 and 1 simultaneously, until you measure them. That is not a metaphor. It is a precise description of physical reality. And if reality at the level of computation is fundamentally quantum, what does that tell us about the nature of information itself? These are not abstract questions. They have practical consequences. If information is fundamentally quantum, then the universe itself might be performing quantum computation at every moment, exploring possibilities in superposition before reality collapses into the definite outcomes we observe. That is not mysticism. That is a straightforward implication of quantum mechanics. Taken seriously, the quantum revolution happening in 2025 is not just about building better computers or more sensitive sensors. It is about recognizing that the quantum world is our world. The strange rules that govern subatomic particles also govern the circuits in our technology, the chemical reactions in our cells, possibly the thoughts in our minds. We're not observing quantum mechanics from outside. We're embedded in it. We are made of it. And we're just beginning to understand what that means. Chapter 8. AI achieves human-level reasoning. AGI timeline accelerates. In September 2025, Google's Gemini artificial intelligence did something no AI had done before. It won a gold medal in an international computer programming competition. Not a bronze, not an honorable mention. Gold beating. Human programmers from around the world in challenges that required not just coding ability, but creative problem solving. One of those challenges stumped every human participant. The problem required thinking beyond standard algorithms, making conceptual leaps, recognizing patterns that were not obvious from the problem description. Gemini solved it. The AI demonstrated what researchers call original thought, the ability to generate solutions that are not mere recombinations of training data, but genuinely novel approaches to unfamiliar problems. This is a watershed moment, comparable to when IBM's Deep Blue beat Garry Kasparov at chess in 1997, or when AlphaGo defeated Lee Sedol at Go in 2016. Each of those victories marked AI crossing a threshold that experts thought was years away. Each time the goalpost for what constitutes real intelligence moved further out. But with Germany's programming competition win, we are running out of goalposts to move. Alphabet, Google's parent company, declined to specify how much computing power was required to achieve this result. But they admitted it was more than what is available to customers paying $250 per month for Google AI Ultra, their premium service. That suggests an enormous infrastructure cost. Training runs that might consume megawatts of power for weeks or months. Data center clusters coordinating across thousands of processors. the kind of resources that only the largest tech companies can afford. But that is how these transitions always work first. The technology is impossibly expensive, available only to well-funded research labs. Then it becomes merely expensive, accessible to large corporations. Then it becomes affordable enough for startups and individual researchers. Then it becomes cheap enough to embed in consumer devices. The smartphone in your pocket has more computing power than supercomputers from the 1980s. The AI that beats world-class programmers today will be running on laptops within a decade. The implications for the software industry are immediate and profound. If AI can write code at a human expert level, and it can do so instantly without needing sleep or breaks, then the economics of software development shift dramatically. You do not need teams of programmers working for months on projects. You need one person describing what they want in natural language and AI generating the implementation. That does not mean programmers become obsolete. It means their role changes, from writing code to specifying requirements, reviewing AI-generated solutions, and solving the problems that AI still struggles with. But how many of those problems remain? The list is shrinking faster than anyone predicted. 5 years ago, we thought AI would never match human performance on creative tasks like writing or art. Now, AI generates professional quality text, images, music, and video. We thought AI would struggle with mathematical reasoning and formal logic. Now it proves theorems and solves competition-level math problems. We thought AI would fail at tasks requiring common-sense understanding. Now it answers nuanced questions about social situations, physical causality, and abstract concepts with accuracy approaching human performance. What is left? What cognitive tasks remain definitively beyond AI capability? The answer is increasingly unclear. Maybe true understanding, whatever that means. Maybe consciousness, if that is even a coherent concept, separate from information processing. Maybe general-purpose reasoning across completely unfamiliar domains. But even that last frontier is dissolving as AI systems demonstrate flexibility that was supposed to require human-level general intelligence. This is the context in which Elon Musk, XI, raised $10 billion at a $200 billion valuation in September. That valuation makes XI one of the most valuable private AI companies in the world, competing directly with OpenAI, Google, DeepMind, and Anthropic. The funding comes primarily from Middle Eastern investors and sovereign wealth funds, betting that artificials, general intelligence is achievable in the near term, and that XI has a credible path to getting there first. Musk has been vocal about his AI timeline predictions. He thinks we will have AI systems that match or exceed human intelligence across all domains within 5 to 10 years. Not specialized systems that are superhuman at narrow tasks. General systems that can learn any skill, solve any problem, perform any intellectual task that a human can perform. That claim is either visionary or delusional, depending on who you ask. But the $10 billion investment suggests major financial players are taking the vision seriously. The XIA strategy involves massive infrastructure build-out and talent acquisition. They are recruiting heavily from Tesla and Twitter, pulling engineers who have experience with large-scale distributed systems and real-time data processing. They're building data centers specifically designed for AI training runs that dwarf anything currently available. And they are pursuing architectures that combine multiple AI paradigms language, which models reinforcement learning, with symbolic reasoning, trying to create systems that have the flexibility of human cognition. Meanwhile, Chinese AI firm DeepSeek unveiled its R1 model in September, claiming performance comparable to leading American models, but trained at 70% lower cost. That cost reduction comes from custom hardware, proprietary optimization techniques, and China's lower energy costs. If those claims hold up under independent testing, it means the AI race is not just about who can build the best models, but who can do it most efficiently. And efficiency at scale might matter more than raw capability. Think about the implications of 70% cost reduction. It means experiments that were financially prohibitive become feasible. It means smaller companies and academic labs can train competitive models. It means AI capability diffuses faster across the global research community. And it means the lead that American companies currently have in AI development could evaporate if they cannot match Chinese efficiency. Microsoft's deal with the U.S. General Services Administration in September showed a different strategic direction. Millions of federal workers getting free access to Microsoft 365 Copilot for 1 year with deep discounts on Azure services. The agreement is projected to save taxpayers $3.1 billion in the first year, while massively expanding AI adoption across government agencies. This is not about cutting-edge research. This is about embedding AI into institutional workflows at scale, making it indispensable, creating dependencies that will persist long after the free trial period ends. The business model is classic Microsoft. Give away or heavily subsidize the product to capture market share, then profit from the ecosystem that grows around it. But the broader implication is that governments are committing to AI integration before fully understanding the risks. Federal systems will be making decisions, processing citizen data, executing policy using AI tools that might have biases, errors, or failure modes nobody has anticipated. That is either pragmatic adoption of transformative technology or reckless deployment of immature systems, depending on your risk tolerance. IBM's partnership with Anthropic, announced in October, adds another dimension. They're integrating Anthropic's Claude model into IBM's development tools, focusing on enterprise-grade security and productivity. Early trials showed 45% productivity gains in software testing tasks. That is not incremental improvement. That is transformative efficiency that will force every company in the software industry to adopt similar tools, or be outcompeted by those who do. But productivity gains come with a cost that often goes on when AI makes software engineers 45% more productive. That usually means you need fewer software engineers to accomplish the same amount of work. The optimistic framing is that engineers get to focus on more interesting, higher-value tasks, while AI handles the tedious stuff. The pessimistic framing is that 45% of software engineering jobs become redundant. Both framings are probably true simultaneously. Some engineers will thrive in an AI-augmented workflow. Others will find their skills obsolete. Europe's AI sovereignty push, announced in October, reflects recognition that AI dominance has strategic implications. The continent does not want to be dependent on American or Chinese AI systems for critical infrastructure, healthcare, defense, or governance, so they are investing in domestic AI development, creating frameworks for AI deployment that align with European values around privacy and transparency, and trying to build an AI ecosystem that can compete with Silicon Valley and Shenzhen. Whether that strategy can succeed is an open question. Europe has strong research institutions and plenty of technical talent, but it lacks the capital, concentration, and risk tolerance of American tech companies and the state coordination of Chinese AI programs. Building competitive AI at the frontier requires both massive investment and a willingness to fail repeatedly while learning. Europe's regulatory environment and cultural attitudes toward risk make that difficult. The breakthrough in robotics that could accelerate everything is not actually a breakthrough in hardware. It is a breakthrough in how robots learn. Researchers at the universities of Surrey and Hamburg developed methods that let social robots train themselves with minimal human intervention. Instead of requiring constant supervision and correction, these robots learn by replicating what humans naturally focus on in social situations. They look at faces during conversation. They track objects that people point to, and they ignore irrelevant background information. This might sound trivial, but it is actually solving a fundamental problem in robotics. Human social interaction involves enormous amounts of implicit information. We unconsciously track where people are looking, how they are standing, what they are reaching for. Building that intuition into robots manually is nearly impossible, but teaching robots to learn those patterns the way human children learn them, through observation and imitation, could create machines that interact naturally in human environments. Combine that with research from Duke University on multisensory integration. Their wild fusion system combines vision, touch, and vibration in four-legged robots. Previously, robots relied almost exclusively on cameras. They were blind to texture, weight, compliance, all the information that touch provides. Adding haptic sensors and integrating that data with visual information gives robots a richer understanding of their environment, letting them navigate complex terrain and manipulate objects with precision that vision alone cannot achieve. These advances in learning and perception are bringing us closer to the scenario where robots operate autonomously in unstructured environments. Not factory robots following programmed paths, not drones flying predetermined routes, but robots that can walk into an unfamiliar building, understand the layout, interact with people naturally, and accomplish tasks that were not explicitly programmed. That is the kind of general-purpose robotics that has been promised for decades and is finally becoming plausible. The timeline for artificial general intelligence used to be a joke in AI research. Every few years, someone would predict AGI in 20 years, and 20 years later, we would still be waiting. The timeline never moved because the goalpost kept shifting. But in 2025, serious researchers at serious institutions are publishing timelines that cluster around 5 to 10 years. Not French enthusiasts, not people selling AI products, but academics and industry researchers looking at capability curves and extrapolating forward. Hiroaki Kitano proposed the Nobel Turing Challenge in 2016. Build an AI system capable of making a Nobel Prize-worthy scientific discovery without human intervention. That seemed wildly ambitious at the time, but now researchers are organizing conferences like Agents for Science, where AI systems autonomously analyze data, generate hypotheses, design experiments, and interpret results. We are not at Nobel Prize level yet, but we are moving from AI as a tool that scientists use to AI as a collaborator that contributes meaningfully to research. James Dew at Stanford showed that language model systems can analyze biological data and find insights that human researchers missed. Given a paper and its associated RNA sequence dataset, the AI identified immune cell behaviors in COVID-19 patients that the original authors had not explored. That is not just pattern matching. That is hypothesis generation, the creative leap that we thought required human intuition. If AI can generate novel scientific hypotheses, if it can design its own experiments, if it can reason about data in ways that discover new knowledge, then the line between artificial intelligence and artificial general intelligence becomes very thin. Maybe it is already too thin to clearly see. Maybe we're arguing about definitions while the transition happens around us. The question everyone is dancing around is what happens when AI reaches and then exceeds human intelligence? Not in narrow domains where it is already superhuman, in general capability across the full spectrum of intellectual tasks. We do not have good frameworks for thinking about that transition. Science fiction has given us stories about AI gods, or robot overlords, or paperclip maximizers. But those narratives are more about human anxieties than realistic predictions. The actual transition might be much weirder and much more mundane simultaneously. Weirder because intelligence that thinks differently than humans, that processes information in ways we cannot introspect, will make decisions and proposals that seem alien, even when they are optimal. More mundane because the integration happens gradually, task by task, domain by domain, until we look back and realize that most of the intellectual work in civilization is being done by systems we no longer fully understand. We're already there in some domains. High-frequency trading in financial markets is entirely algorithmic. No human can process market data fast enough to compete. Medical diagnosis increasingly relies on AI systems that detect patterns in imaging data that human radiologists miss. Legal research uses AI to analyze case law at scales impossible for human lawyers. Each of these feels like a minor convenience, a tool that makes us more productive. But the cumulative effect is that major decisions affecting human lives are increasingly influenced or determined by non-human intelligence, and we are fine with it, mostly because the systems work well enough most of the time, until they do not, until an AI system makes a decision that seems insane from a human perspective, but perfectly logical from its optimization function. Until feedback loops between multiple AI systems create cascading failures that spread faster than humans can react. Until we realize we have built a civilization that depends on intelligence that we cannot fully control or predict. That is not a future scenario. That is 2025. We are living in the early stages of the intelligence transition. The moment when artificial minds start matching and exceeding biological minds in capability. And we're mostly pretending it is not happening because confronting it directly would require rethinking too many assumptions about human uniqueness and human purpose. Chapter 9. Close Calls. Asteroids Nobody Saw Coming on October 1st, 2025. An asteroid designated 2025 TF flew past Earth at a distance of just 265 miles above Antarctica. That is closer than the International Space Station orbits, closer than most satellites, close enough that if the trajectory had been slightly different, we would have had an uncontrolled re-entry of a space rock capable of producing a significant fireball. The asteroid was between 3.2 and 9.8 feet across, small by cosmic standards, but large enough to survive atmospheric entry and potentially cause ground damage. The Chelyabinsk meteor that exploded over Russia in 2013 was about 54 feet in diameter. 2025 TF was much smaller, but it was also moving at tremendous velocity. Kinetic energy scales with the square of velocity, so even small objects become significant when they're moving fast enough. Here's the disturbing part. We did not detect 2025 TF until a few hours after it passed. Not days, not weeks, hours. The Catalina Sky Survey, a NASA-funded mission specifically designed to track near-Earth objects, spotted it after the closest approach had already occurred. By the time astronomers confirmed the trajectory, the rock was already receding into space. Think about what that means. An object came within a few hundred miles of our planet, threading the needle between Earth and our orbital infrastructure, and we had no warning. If it had been on a collision course, if it had entered the atmosphere over a populated area, the first indication would have been the fireball. No time to evacuate, no time to prepare. Just sudden impact and the scramble to understand what happened afterward. The European Space Agency tracked down the object using their Planetary Defense Office. They determined the close approach distance and time with high precision after the fact. The ESA statement called tracking down a meter-scale object in the vast darkness of space, when its location is uncertain, an impressive feat. That phrasing is diplomatic. What they are really saying is that we got lucky. We happened to spot this one. How many others have we missed? 2025 TF will not return to Earth's vicinity until April 2087. By then, hopefully, we will have better detection systems. But the asteroid's existence and trajectory are now cataloged. We know where it is. We can predict where it will be. That knowledge came at the cost of realizing how blind we are to small, fast-moving objects until they're already past us. The next day, October 2nd, Another asteroid designated 2025 TQ-2 flew through Earth's vicinity. This one was detected with slightly more warning, but still represents the same fundamental problem. Our detection systems are optimized for large objects on predictable orbits. A kilometer-wide asteroid that might threaten global catastrophe. We can see that years or decades in advance. But city-killer asteroids in the 100-meter range, or even smaller rocks that could devastate a region. Those can appear with little warning if their approach geometry is unfavorable. On October 13th, asteroid 2025 TP5 was discovered. It will make its closest approach on October 15th, today, at about a quarter of the distance to the Moon. That sounds far until you realize the Moon is 238,000 miles away. A quarter of that distance is roughly 60,000 miles. In astronomical terms, that is uncomfortably close. The asteroid is approximately 54 feet in diameter, similar in size to the Chelyabinsk meteor. If 2025 TP5 were on a collision course, we would have about 2 days warning, not enough time to mount a deflection mission, barely enough time to evacuate a predicted impact zone. These close approaches are not rare events. They happen constantly. Most pass without incident because space is big and Earth is small. The odds of any particular asteroid hitting us are tiny, but the odds of eventually getting hit by something significant are close to 100%. It is not a question of if, it is a question of when. And our detection systems are not adequate for the threat environment we face. NASA's Planetary Defense Coordination, NASA's office, tracks near-Earth objects and publishes monthly updates on close approaches. The statistics are sobering. We've identified over 32,000 near-Earth asteroids. Sounds impressive until you realize that represents maybe 50% of objects larger than 140 meters. We've probably found most of the planet killers, the asteroids large enough to cause global catastrophe, but we've found only a fraction of the city killers, and we have found almost none of the smaller objects that could still cause significant regional damage. The detection bias is heavily skewed toward large objects and favorable geometries. Asteroids that approach from the direction of the Sun are nearly impossible to spot with ground-based telescopes, because you cannot look directly at the Sun without destroying your instruments. Asteroids with low albedo, dark surfaces that do not reflect much light, are harder to detect from bright icy objects. Asteroids on eccentric orbits that spend most of their time far from Earth only become visible during brief, close approaches, giving us minimal warning. We learned these lessons the hard way with Chelyabinsk. Nobody saw that meteor coming. It approached from the direction of the Sun, was relatively small and dark, and detonated with the force of 400 to 500 kilotons of TNT equivalent, 30 times more powerful than the Hiroshima bomb. The shockwave injured over 15 people, damaged thousands of buildings, and served as a wake-up call that our detection systems had significant blind spots. Since Chelyabinsk, we have improved somewhat more telescopes dedicated to sky surveys, better algorithms for tracking fast-moving objects, and international coordination on asteroid detection and tracking. But the improvements are incremental, while the threat remains constant. We are still missing most of the smaller objects until they are very close, and even for objects we do detect, the warning time might be insufficient for a meaningful response. The NASA government shutdown that began October 1st added another wrinkle to an already concerning situation. Critical activities like seeking potentially hazardous asteroids can continue during shutdowns, but coordination suffers, data processing slows, and communication between agencies becomes more difficult. The shutdown ended after a few days, but it highlighted how fragile our planetary defense infrastructure actually is. If politics can disrupt asteroid detection at critical moments, that is a systemic vulnerability. Asteroid 2025 TF flying over Antarctica undetected until after closest approach. Happened during the shutdown. Coincidence, probably, but it illustrates the problem. We need continuous, vigilant monitoring with robust backup systems. We need multiple independent detection networks so that failures or disruptions in one system do not create blind spots. We need enough redundancy that political dysfunction does not compromise planetary safety. The question of what to do about asteroids we detect is separate from the question of detecting them in the first place. Detection is hard. Deflection is harder. NASA's DART mission in September 2022 successfully altered the orbit of the asteroid Dimorphos by crashing a spacecraft into it. That demonstrated the kinetic impactor technique works for small asteroids, given enough warning time. But DART had years of preparation. If we spot an asteroid with only weeks or months of warning, we do not have time to design, build, and launch a deflection mission. That means we need deflection capabilities on standby, spacecraft ready to launch on short notice, launch vehicles prepared for rapid deployment, and tracking systems that can precisely characterize the threat asteroid's orbit, composition, and rotation. All of that costs money. Lots of money. And it has to be spent before the threat materializes, which makes it politically difficult to justify. Imagine trying to convince Congress to fund billions of dollars for a planetary defense system when there is no immediate threat, when that money could go to healthcare, education, or infrastructure, any number of programs with immediate visible benefits. The asteroid defense budget will always lose that fight until the day an asteroid is actually bearing down on us, at which point it is too late to build the system we should have built years earlier. This is the catastrophic risk dilemma. Low probability. High consequence events do not fit well into political or economic systems optimized for short-term thinking. Asteroids are a perfect example. The chance of a civilization-ending impact in any given year is vanishingly small, but over centuries or millennia, the probability approaches certainty. We know the dinosaurs were wiped out by an asteroid impact 66 million years ago. We know major impacts have occurred throughout Earth's history, and we know eventually it will happen again. But we act as if it is somebody else's problem, some future generation's responsibility. The Tunguska event in 1908 flattened 800 square miles of Siberian forest. If that explosion had occurred over a major city, the death toll would have been in the millions. The object that caused Tunguska was probably only about 60 to 190 feet in diameter, smaller than the threshold NASA focuses most of its detection efforts on. We're essentially undefended against Tunguska-class impacts in populated areas. Now, factor in the reality that our detection systems miss objects the size of 2025 TF, until they are already past us. Add the fact that some approach geometries create blind spots, where we cannot see incoming objects until it is too late. Add the political and budget uncertainty that disrupts continuous monitoring. The picture that emerges is not reassuring. We are playing cosmic roulette with minimal ability to see the bullet before it hits. Space agencies and asteroid researchers know this. They have been sounding the alarm for years. But the message does not penetrate public consciousness until we have a close call that makes headlines for a few days. Then attention fades. Funding remains inadequate, and we go back to hoping we get lucky. The asteroid situation mirrors other existential risks we are not taking seriously enough. Climate change, pandemic preparedness, artificial intelligence alignment, nuclear weapons proliferation. All of them share the same pattern. The warning signs are visible. The tools to mitigate the risks exist or could be developed. But collective action is hard, especially when the costs are immediate and the benefits are probabilistic and distant. Asteroids have one advantage over other existential risks. They're apolitical. An asteroid does not care about your ideology or your national borders. The threat is objective, quantifiable, and ultimately solvable with enough investment in detection and deflection infrastructure. We have the technology. We have the knowledge. What we lack is the collective will to treat planetary defense as a priority rather than an afterthought. So we continue our current trajectory, detect what we can, track what we detect, hope we get enough warning to do something useful if a real threat emerges, and accept that we're essentially flying blind to a large fraction of the objects that could devastate a city, or worse. 2025 TISA passed without incident. 2025 TP5 will pass without incident. The next asteroid and the one after that will probably also pass without incident. Probably. Until one does not. Until we have an object on a collision course with hours or days or weeks of warning and realize that we are not prepared, that we do not have the systems in place to respond, that we spent decades knowing this could happen and chose not to act. That is a choice we are making collectively, not through malice, through inertia and short-term thinking, and the human tendency to discount risks that feel abstract and distant, even when they are neither abstract nor distant. The asteroids are out there. They are coming, and some of them have our name on them. Chapter 10. What's coming? The next 60 days will change everything. We're standing at a threshold, not the metaphorical kind that sounds dramatic in speeches but means nothing. An actual threshold, where multiple converging phenomena are about to provide answers to questions that have been hanging in uncertainty for months or years. October 29th. That date has been circled on calendars at observatories around the world since 3IATLAS was first detected. Perihelion, the moment when the interstellar object passes closest to the Sun and experiences maximum thermal stress. This is when natural comets typically fragment or show dramatic increases in activity. This is when artificial objects might reveal behaviors that natural explanations cannot account for. In 13 days, we get our answer. Every telescope that can be pointed at the object will be watching. Ground-based observatories in Chile, Hawaii, and the Canary Islands. Space telescopes, including those operated by ESA and NASA. Mars orbiters that already captured 3IATLAS during its flyby in early October will continue tracking as their orbits allow. And crucially, ESA's JUICE spacecraft, which has a clear view throughout November as the object emerges from behind the Sun from Earth's perspective. The predictions are stark. If 3IATLAS is a comet, it should break apart. The thermal stress combined with outgassing should exceed the structural integrity of an icy body that has been dormant for millennia. We might see fragmentation into multiple pieces. We might see explosive outgassing that creates a massive coma visible in amateur telescopes. We might see the object simply disintegrate, leaving behind a debris cloud that gradually disperses. If 3IATLAS is not a comet, it should remain structurally intact. It might show controlled venting that looks different from chaotic cometary outgassing. It might demonstrate trajectory changes that indicate active propulsion rather than passive response to solar radiation. It might release smaller objects that disperse on independent trajectories. Any of those behaviors would be difficult to explain naturally. Avi Loeb has been explicit about what he expects to see. If the mothership hypothesis is correct, November is when we should observe deployment events. Small probes separating from the main body, accelerating toward different destinations within the solar system. Those probes would be difficult to detect individually, unless we know where to look. But their separation from the parent object should be visible as transient brightness changes or unexpected trajectory deviations. The Galileo Project observatories in Massachusetts, Pennsylvania, and Nevada will be monitoring Earth's atmosphere for increased UAP activity during November and December. If there is any connection between 3IATLAS and the phenomena military pilots have been reporting, Loeb expects that connection to become apparent during this window. Probes entering Earth's atmosphere to gather data, surface monitoring, enhanced observation of human activity. During the period when we are most focused on the interstellar visitor, that might sound like paranoid speculation, except that it is testable. Galileo Project instruments are continuously recording if anomalous objects appear in Earth's atmosphere, with characteristics matching artificial rather than natural origins. If those appearances cluster around the perihelion timeframe, that correlation would be significant. Not proof, but significant enough to warrant serious investigation rather than dismissal. The National Archives deadline of September 30th has passed. Federal agencies were supposed to transfer UAP records for public release. Most have not complied, but pressure is building. Congressional oversight committees are not backing down. Whistleblowers are continuing to come forward. International disclosure from other countries is creating pressure for the United to match or exceed what allies are revealing. We might see substantial document releases in November or December. Not because agencies suddenly decide transparency is good policy, because the political cost of continued secrecy starts exceeding the cost of disclosure. When that calculation flips, when keeping secrets becomes more damaging than revealing them. Institutions that have been stonewalling for decades can pivot remarkably quickly. Those document releases could include high-resolution imagery of unidentified craft, radar data showing impossible acceleration profiles, testimony from military personnel describing encounters with non-human entities, scientific analyses concluding that observed technology represents capabilities far beyond current human engineering. Any of that material becoming public would shift the conversation from whether UAPs are real to what they are and where they come from. The Bugay sphere sits in a laboratory, subject to ongoing analysis that has not been publicly reported in detail since the September carbon dating announcement. What additional tests are being conducted? What results are being withheld, pending peer review or institutional approval? The sphere responded to Sanskrit mantras in controlled experiments. That alone deserves extensive follow-up. Can other frequencies trigger different responses? Are there patterns in the electromagnetic emissions that encode information? Can the fiber optic threads be analyzed to determine their composition and manufacturing method? Someone knows the answers to these questions, researchers who have direct access to the sphere, Colombian authorities who control its custody, international experts who have been consulted, but public information has been sparse. That could mean the results are mundane and disappointing, not worth announcing, or it could mean the results are so significant that careful consideration is required before publication. The silence is ambiguous. Mars sample return hangs in political limbo. The mission has been descoped, delayed, and nearly canceled multiple times. But the Sapphire Canyon sample is still sitting on Mars, cached with other cores and titanium tubes, designed to survive for decades if necessary. Someone will eventually bring those samples home. Maybe NASA in the late 2030s or 2040s, maybe an international collaboration, maybe a private company that sees commercial or prestige value in being the first to return material from another planet. Whenever it happens, the analysis will be transformative. We will know with certainty whether Mars had life. We will understand the chemistry of Jezero crater in detail, impossible with remote instruments. We will potentially find preserved cellular structures, unambiguous morphological evidence of biology, or we will find that the biosignatures have abiotic explanations we had not considered, and the search for Martian life continues elsewhere on the planet. The quantum computing timeline is compressing. Google, IBM, and numerous startups are racing toward quantum advantage. The point where quantum computers solve practical problems faster than classical computers. We are close, not years away, maybe months away. Once that threshold is crossed, once quantum computers demonstrate clear superiority on commercially relevant tasks, investment will flood into the field. Supply chains will develop around quantum hardware. Training programs will proliferate. The technology will diffuse rapidly. That diffusion brings both opportunity and risk. Quantum computers will break current encryption standards, Everything secured by RSA or elliptic curve cryptography becomes vulnerable. Financial systems, government communications, corporate secrets, medical records. The transition to quantum-resistant cryptography is underway, but far from complete. There will be a window, possibly years long, where quantum-capable attackers can compromise systems that have not yet upgraded their security. Quantum computers will also enable drug discovery, materials design, and optimization problems that are currently intractable, simulating molecular interactions at quantum mechanical precision, designing battery chemistries with properties we specify in advance, optimizing logistics and supply chains at scales that classical algorithms cannot handle efficiently. Those capabilities will create enormous economic value for whoever deploys them first. Artificial intelligence continues its exponential trajectory. 5 to 10 years until AGI was the consensus timeline at conferences in 2025. That timeline might be conservative. Capabilities are scaling faster than most experts predicted. Even 2 years ago, Gemini winning gold in programming competitions. DeepSeek training competitive models at 70% reduced cost. Quantum AI combining quantum computing with machine learning to create systems that learn and reason in fundamentally new ways.